Hey, welcome back. Today, we're going to use the information that we collected last time on friction, and we're going to use that to solve simple piping problems. What is it that we have in a simple piping problem is a system where it's essentially a Bernoulli with friction. Um, so in order to solve this, there is sort of a clear guideline of how to solve these problems, where you usually know a change in elevation, the length of the pipe, and the pipe material, and you also know the conditions of the fluid, basically the density and the viscosity. That would imply that you also know the temperature, right? So that you calculate the correct density and viscosity. So all of these are typically known in the system, whether you're designing a piping system for a chemical plant or whatever. There's going to be typically a known elevation, a known length of pipe. Typically, what you're looking for is either one of these three: a flow rate, a diameter, or a pressure drop. And I'll try to explain what those three imply in a system that is, say, existing, and you are putting a pump, let's say, that gives you a certain pressure. The pressure is can be measured, and you are trying to calculate what is the flow rate that you would get at that in that system. That it would be number one. The looking for the flow rate is typically on an existing system. You're trying to figure out what would be your flow rate, as opposed to when you're looking for the pipe diameter. It's typically a system where you know what the pressure will be, you know what flow rate you need, and now you're trying to size that pipe so that you can install it. So this is more of a design effort when you're trying to find the pipe diameter. And kind of related to that would be that you know the pipe diameter and you know the flow rate, but you're trying to find the right pump that would give you a right pressure so that you can deliver the right amount of velocity or flow rate into your system. In all of these problems, we're going to be using an energy balance. And you can see it here. First of all, we had defined this separately um, from the combination of the energy balance with the momentum balance. But now we're going to be mostly using this right here, which is now our definition of the frictional dissipation as 2FF L over d um squared. And we're going to then assume that there is a pressure drop and that there is a height difference in between the two um, in order to do these calculations. Note that in this system, we do not have a velocity 1 minus velocity 2. And that is because in this simple piping problem, we're assuming that we have a pipe of the same diameter, and therefore the velocity at point 1 and the velocity at point 2 are the same. There could be complications and changes in pipes, and I'll give you a little snip of what that looks like at the end of this class. So, out of those three options, looking for pressure drop, looking for a diameter, or looking for a flow rate, the easiest one is to find a pressure drop. And before we go into it, you will see that I'm going to remind you that we're trying to solve this problem here. And to get the friction factor, I need to have my Reynolds number. And to have my Reynolds number, I need to have my velocity, right? And I also need my diameter of the pipe. So whenever I don't know flow rate or diameter, I don't know my friction factor. And that implies that it becomes a little bit more difficult to solve the first two cases versus the third, where basically I'm just looking for this. I can find my friction factor easily and then solve for the delta pressure. So that's what we're going to do first, to try to solve for an unknown delta P. First step is that we calculate velocity from a flow rate if that was not available. Then from that velocity, we will get our Reynolds number. And we're assuming that we know the diameter of the pipe and fluid properties, so we can calculate that Reynolds number. Then we get the roughness ratio. The problem should give you at least the material of the pipe so that we can get the roughness, and then we divide it by diameter. Then we're going to get the friction factor. And the friction factor can be found in three different ways. If it's laminar, we're going to use the equation that we derived earlier of friction factor equals 16 over Reynolds. If it's turbulent, we either use the chart of the fanning friction or the equations that we derived. Then we can compute the pressure drop with the equation above. And this is the easiest, as I said. In our typical book for fluid mechanics, there are these three examples. They are essentially the same example. It's just the example solved in three different ways. One for a pressure drop, one for a flow rate, and one for a diameter. It is essentially a pump that is transferring crude oil from a tanker to a storage tank. There is an effective length of 6,000 feet of commercial steel. The discharge is 200 feet above the pump, and the tank is in a hill, so there is a higher point, and then losses between the tanker and the pump can be ignored. Then we're given the density of the crude oil, the viscosity of the crude oil in centipoise, and the vapor pressure, which we are not going to use for this problem. So I'm going to first try to draw this here. So we have at C, this is my C, an oil tanker. And that oil tanker is delivering that oil tanker has a bunch of oil here, and that oil is taken out with a pump, and that is driven up and across a hill into a storage tank. Okay. This is oil. This is my pump. The equivalent length of this thing is 6,000 feet of commercial steel. The distance between the oil, it basically says, let me see, back here, 200 above the pump. So from here to here, there's 200 feet above the pump. It told us that we have, that's it. And so for specific for 3.2, there is an additional information. The diameter, which is a 6-inch NPS Schedule 40 commercial steel. And the flow rate, which is 506 gallons per minute. We're going to have to do a lot of conversions for this one, of course. So how do you solve a problem like this? Well, that's what we have here, right? A little bit of a a guideline, but there are a few things that we would have to do first, and it's good to collect a little bit of more information. To do that, I'm going to go back here so that we can find I don't have it in this figure, but in this table. But a 6-inch schedule 40, I will give you here what the value is. The diameter is 6.065 inches for a 6-inch schedule 40 inner diameter. The roughness of commercial steel is 0.00015 foot. Now we need to also calculate our flow rate, right? Our velocity. Where our mean velocity equals Q over A. Now that I have the diameter, I can do this calculation. First, you note that I now have a little bit of a mess of units. So I'm going to do on the top a conversion of 506 gallons per minute into cubic feet per second, where 1 minute is 60 seconds and 1 cubic feet is 7.48 gallons. See, that gives me feet per second cubic feet per second. And then I divide this by the diameter, but I'm going to convert this here before we continue, saying that 1 foot is 12 inches so that I have everything in feet. This is 0.5054 feet. So I can now do the area as pi over 4, 0.5054 feet squared. That would give me a velocity of 5.62 feet per second. The second step after this is calculating our epsilon over d, and I have this already in the right units. So I can just do the division between these two, and that gives me 0.000297. Finally, I'm going to calculate the Reynolds number. And the Reynolds number is raw velocity diameter over mu. Keep in mind that Reynolds is unitless, so I need to cancel out all the units here. So 53 pound mass per cubic feet, 13.2 centiboys. So 53 pound mass per cubic feet. Multiply by a velocity of 5.62 feet per second. And a diameter, 5054 feet. Divided by 13.2 centiboys. Now a centiboys is equal to 0.000672 pound mass per feet second. And that is the conversion that we need to do in order to cancel out all these units. Okay? That gives me 16,790. And that means that this is a turbulent flow. When you have a turbulent flow, unfortunately, we cannot use our typical equation of 16 over Reynolds for laminar flow. Therefore, we need to go and do calculations of what is our friction factor using the Fanning diagram. So Let's go back a little bit so you can see the fanning diagram. We had done that equation, that example before. Now, we have a Reynolds number of 16,000. This is 10,000 here, and this is 20,000. So 16,000 sits somewhere around the middle. Also, we have a roughness of 0.000297, which is somewhere around here, right? In between this line and this line, it would be an extra line that will go through here. It really doesn't matter because we're trying to get up here, and you see that all these lines eventually converge into almost the same place, right? So when we get here, we are somewhere around here, right? And that's a fanning friction factor of 0.007. With the equation, we can find that the fanning friction factor, so kind of putting these two together, we can find that the fanning friction factor is actually 0.00692, a little bit lower than what you can find with the graph. But it doesn't matter. The error is very small between the calculation with the graph and the calculation with the equation. If I go back here now, this is where we're at, and now we can compute the pressure drop using the equation above, right? I'm going to do it in a slightly different way. So I'm going to give you our typical energy balance. And to that, let me go back here and tell you where are we going to do that balance from, right? The problem is being asked, that we're being asked is, what is the pressure at the exit of my pump? And so that would be number 2 here. This is a number 1. That would be a number 2. We typically have an exit over here, number 3. So if I look at points 2 to 3, I can do a simple piping problem because the pump is not included. So I don't have to add a pump between points 2 and 3. At point 2, there is a high pressure because the pump provided a higher pressure. And that's what we're going to try to solve, the pump drop between points 2 and 3, the pressure drop between points 2 and 3. So to do that, I'm going to write an energy equation between points 2 and 3. G, and I'm going to add my frictional dissipation term, which is 2FF L over D UN squared. If you look at the equations and follow closely, what we have here is 2FF L over DUM squared times rho. But that rho in my equation is down here, is under the pressure. You see? Now, between points 2 and 3, because it's the same pipe, we have the same velocity. So I can cancel these two velocities being the same. I can also assume that point 2 is 0, and then point 4 is the 200 feet. And I can also assume that point 4 is 0 gauge. So that then P2, which is the pressure that I'm looking for, is C4G times raw plus 2FF raw L over D squared. So now all I need to do is put those numbers together, right? 200 feet, 32.2, the 53 pound mass per cubic feet, 2, 0.00692. That's my FF times 53 pound mass per cubic feet. That is my raw. Multiplied by 6,000 feet of length of pipe divided by 0.5, no, 5054. That's my diameter. And finally, my velocity squared, 5.62 feet per second squared. So that I get P2. All that I now, if you follow the numbers, I'm going to end up on pound mass per feet second squared. And so I'm going to now take all that and divide it by 32.2. And that's basically 1 pound force equals 32.2 pound mass feet per second squared. And so that P2 gives me 19,137 pound force per square feet, which is also written as PSF. If I want it in PSI, pounds per square inch, I say that a feet square is 144 inches squared, right? And that gives me 132.9 PSI gauge. It is somewhat important to include gauge there so that you know that it's pressure above atmospheric. And that's because we assume that P4 is 0. So 132 is a pretty high pressure that this pump needs to deliver and that pipe needs to withhold. So you need a very strong pipe in order to get that flow going. Now, there is, this is basically a different, just calculations here. Let's say that you now have the pipe is still 6-inch NPS schedule 40. And you have now a pump. And the pump delivers the pressure that we have. Then what would be the flow rate? And so you know the answer. The flow rate is the same flow rate, 506 gallons per minute, because obviously everything else is the same. But let's go over how to find that information. Because here's the problem. I have my inner diameter. I can calculate 0.5054 feet as my inner diameter, which means that I have my epsilon over D. 0.000297. The problem is that I don't have a Reynolds number. Not having a Reynolds number creates a problem. I do not have my friction factor. If I don't have my friction factor, then I cannot calculate, I cannot do any calculations, right? I cannot go back to the energy balance to solve for the velocity. So what is it that we need to assume? Well, we can either start assuming a laminar flow, if you think it might be laminar, but we need to start with an estimate of either the Reynolds number or the velocity. Because the velocity is what we don't know, right? So when you look at these, here's what I typically recommend my students to do. You see that over here, a little bit past around this area onwards, the Reynolds number does not affect the friction factor. If you have a roughness ratio of 0.01, all of these Reynolds number give you the same value of the friction factor, which means that it doesn't matter if you put 10 to the 5 versus 10 to the 6 or 10 to the 7, you're always going to get the same friction factor. Therefore, what I typically recommend is that we start somewhere in this region of variability. Therefore, if we are wrong and we need to go this way, then we are going to get to the real value faster. If we're going this way, we're going to get to the real value also quite quickly. So we're going to assume a value of Reynolds, and we're going to have to do iterations. Iterations involve getting a value, assuming a value of Reynolds. With that value of Reynolds, we're going to go through the exercise of getting a fanning friction factor and solving the energy equation for velocity. Now, that velocity would be the correct velocity only if your estimate of Reynolds was correct. But you know it's not really correct because you just made it up. So what we're going to do then is that with that new velocity, we're going to recalculate the Reynolds number. And we're going to do that in a circular way in which we find a Reynolds number. From the Reynolds number, we get the friction factor. From the friction factor, we solve the energy equation. The energy equation gives us a velocity, and the velocity is used for the Reynolds number. And you can go over this roundabout until the velocity doesn't change. And that means that that is the real velocity. You have converged into the real value of the velocity. Okay? So in this case, we are assuming 100,000. Like I told you, let's start somewhere in the middle. In this case, we started here at 100,000. We have an epsilon over d, like we said, over down here. Now, by the way, you know that the Reynolds number is 16,000. So we are starting 5 off on this on the Reynolds, right? We're off by a factor of 5. That value here is, as you can see, that intercept here is around 0.0049. With the equation, you get 0.0048. Now, we have the friction factor. We have L over D. We have the delta height. And we have the delta pressure is given here. Therefore, we can solve for velocity. That's a calculation of velocity. You don't have to do it all at once like I did here, but there's the diameter, the friction factor, 53 pound mass per cubic feet, 6,000 feet of pipe, the delta P, which is 132 PSI gauge, but then we multiply by 144 to change it to feet squared, and then we multiply by 32.2 to convert the pound force to pound mass feet per second squared. And the same here, 53 times 32.2 times 200 feet difference. All that to give you 6.68 feet per second. Now, if you go back to our previous problem, you remember that our velocity should be 5.6. So even though our Reynolds number was off by a factor of 5, our velocity is not really that off, right? It is just off by about 20, 30%. So now with this new velocity, I now recalculate our Reynolds number. And we get 20,175. Much better, right? Much closer to where we're supposed to be. Let's go back here. This is 10,000. This is 20,000. So we're somewhere around here, a little bit higher than here. So I'm going to throw that line again. And it's going to intercept with a line that comes here to give me a value of somewhere around 0.06, 0.065 or so, right? Oh, let me show you here how the iterations go. We started with 100,000. We got a friction factor of 0.00488, and we got a velocity in feet per second of 6.68. With that 6.68, we recalculated a Reynolds of 20,175. That gave us a friction factor of 0.0066. And the velocity went down to 5.73. With that 5.73, we can calculate a new Reynolds number, 17,301, which gives a slightly higher friction factor and a value of 5.63. And at that point, you see that the velocity is not changing that much. That difference between those two is about 5%. So let's do it one more time. You see that now in my last iteration, the Reynolds number barely changed. So that means that my friction factor is not going to change much and my velocity doesn't change almost at all. So therefore, I know my velocity, 5.62. There might be some error. That is the velocity that we had originally in the problem. But as you're doing these iterations, you might have some error from calculating the friction factor, reading the fanning diagram, etc. And that is fine. I always say that in these calculations, there's other factors that contribute more to error than your own calculation on errors and iterations. Like, for example, the roughness of the pipe is not exactly the roughness that you will find on the table. And there's some variability on those, and there's going to be corrosion of that pipe over time, so the roughness changes. All of these contribute to errors in calculations of fluid mechanics that are much higher than getting a little bit of a 1% or 2% error on your velocity calculation. Okay, so that's how you solve this type of problem through iterations. A little bit more difficult is when you now don't know the diameter. The problem with not knowing the diameter is that the diameter depends, the velocity depends on the diameter. So we don't have a velocity nor a diameter at this point. So you can assume a diameter. With the assumed diameter, you calculate the velocity. You can calculate an epsilon over d and a Reynolds number. You can get now a friction factor. And now comes the difficult part. Is going into this equation, you will think that you're going to solve for diameter to get a new diameter and do the iteration again with a new value of diameter. But you have to remember that this value of velocity, this q over a, which equals to Q over pi over 4 diameter squared. All that is squared, right? So this term of velocity has a diameter to the power of 4 in the denominator. And so you can either try to solve all that and then solve for the diameter using that equation, or as I typically do is I solve for velocity and then I calculate the diameter that gives me that velocity and then do the iterations that way. Okay. So apart from those simple typing problems, I'm going to introduce a little bit of a complication, but sort of an important one, and that's pipe fittings. A pipe fitting is essentially things that are not a straight pipe that introduces some sort of friction loss. What things are those? Well, you can think of elbows, turns, but also valves, things that hinder the flow of the liquid. These are from another book, but kind of more precise. So I kind of like showing these. This is a pipe entrance, a pipe reducer, and it all depends on whether that reducer has a certain angle. So you can think of a very sharp reduction in the pipe size gives you more friction than a smooth one. And so that's what is being calculated there. An expansion, a bend, a smooth bend, all of these will contribute to losses. Not here, but important. Valves. A globe valve versus another type of valve. They have different values of losses. How do we deal with pipe fittings? We're going to assume that the pipe fitting has a length over diameter equivalent. It is essentially saying, in the last problem, we had 6,000 feet of pipe. And let's say that I add an elbow, and we say, well, that elbow is the same as having an extra 100 feet of pipe or something like that, right? But not only length, but length over diameter. And so here's an example of a problem, two pipes connected together, and we're going to try to calculate the difference in the elevation between the two pipes when the velocity is 0.1 cubic meters per, sorry, not the velocity, the flow rate is 0.1 cubic meters per second. It all starts with identification of what are the fittings that we have. One of them was already discussed and is a pipe entrance that has an L over D of 27. This is a pipe entrance right here, and that's basically given an L over D. This is an expansion. And the expansion has a specific equation where the frictional dissipation is U1 minus U2 squared over 2. This over here is also an expansion, but an expansion in which the velocity is at the end is 0. So that frictional dissipation would be U, which I'm going to call U2 because it's of pipe 2, minus 0 square over 2. Okay. We typically calculate U1 based on Q over A. So U1 would be Q1 over A1. You will need to calculate U2, which is Q2 over A2. I won't go into the details of the numerical values, but I wanted to show you this full equation where the frictional dissipation will be equal to a bunch of terms. the term of the pipe entrance, here it is, 2FF, the L over D of the pipe entrance. So this is entrance times the velocity. But we also have the frictional dissipation of pipe 1. Then we have the expansion. That is right here. Then we have pipe 2, frictional dissipation. And finally, we have the second expansion. And you see that we are adding all of these terms. This is essentially a calculation of the complete frictional loss in the system, and it's composed of different terms. In all of that, we're going to end up with a balance, a sort of energy balance between points 1 and 2, where there's C1G, velocity is 0, pressure is 0, is going to be equal to C2G plus a frictional loss. And so I can easily do that calculation if I had the frictional loss defined. And so out of these, we have to obviously calculate a friction factor. So let me go back here. We're going to get these two velocities. Out of these two velocities, we're going to have Reynolds 1 for pipe 1 and Reynolds 2 for pipe 2. They have different velocities, so they have different Reynolds. And from there, we have friction factor 1 for pipe 1 and friction factor 2 for pipe 2. And so when I come here, that friction factor here is not the same as this friction factor here. So this is friction factor for pipe 1. This is friction factor for pipe 2. You add all of these together and then go back to my energy balance, C1 minus C2 times G equals F. And that gives me the distance that I need. Okay? Last problem that I want to discuss. We're not going to solve it, but this problem introduces one important component, is complicating things with a pump. So you can do solve friction problems with a pump in the way. All you need to do is redo your energy balance to include a pump. Now, this problem has a few options, so to speak. You see here that I have a 1 on top of the tank, and I have a 1 out of the pump. And the reason is because I can solve the problem in those two ways. Because the pressure exiting the pump is given, then this point 1 out of the pump is very easily solved. What we are trying to do is to determine the velocity of the ethanol being pumped in a 2-inch Schedule 8 cast iron pipe. You find the diameter using the tables. You find the friction, the pipe roughness based on the material given. And then you calculate an epsilon over D. Obviously, because it's a velocity calculation, requires an iteration. But the first step is to set up an equation. And that would be the equation from top of the tank to the exit, where the top of the tank, it's open to air. So it's an easy 0 velocity, 0 pressure calculation. And all you have is a WP, and that WP is actually given somewhere around here. This is the WP, the energy input to the system by the pump. So it is not that difficult to solve this energy equation with a pipe entrance L over D of 55. Now, if you go from 1 to 2 here, and by the way, this L over D requires you to have 35 feet plus 90 feet, so 125 feet. So that's what I'm calculating here. If you select point 1 to point 2, then you only have a single pipe, no pipe entrance, no pump, right? So that's a much easier calculation where I have P1 over rho that was given, and then C2G and the frictional dissipation term. So P1 over rho equals C2G 2FFL over DUM squared. And then the L over D is calculated with 90 feet. And P1 is 800,000 pascals. Okay. Now, I will leave flow through packed beds for a shorter class. This basically concludes the part of frictional dissipation and fluid in pipes. What we need to do now is to give you a little taste of how to use all this information for chemical engineering equipment. And we decided that the chemical engineering equipment that we're gonna show you would be a packed bed. And so I will do this shorter class on packed beds for your next class. Okay, thank you very much.